go to. Okay, thank you very much. I mean, it's my great pleasure to speak in this Westlake University. I mean, virtually. Hopefully, I could visit the university in the near future. So my title is about K-stability and birational geometry. I mean, as we all know, K-stability was a notion introduced by looking for canonical geometry metric on complex varieties. So what is canonical metric? So let's first look at the simple case that when the dimension is equal to 1. So basically that's just Riemann surface, or our algebraic geometers call it algebraic curves. So in this case, I mean, Poincaré proved this famous uniformization theorem to say that any Riemann surface, compact Riemann surface, it has this 3 form. Either it's CP1 or it's a torus. So basically it's given by C modular lattice, and topologically it's just S1 cross S1, or it's a upper half plane module some discrete group action. So we know that in the first case, it has this, I mean, it's a sphere, so a two-dimensional sphere. So it has a curvature, it has a metric with curvature 1. The second one is flat, so it has a curvature has a metric with curvature 0. And the third one is hyperbolic, because you can just descend the hyperbolic metric from the upper half plane to get some metric with constant curvature -1. So clearly these 3 are the best metric you can look for. So we want to generalize this kind of trichotomy to any arbitrary dimension. So we have, I mean, there are different generalizations, but arguably, I think the deepest generalization is looking at the psi of the chain class. So the CP1 corresponds to the case that the C1 positive, which we call Fano variety. I mean, this is named after Italian mathematician Gino Fano. And the second case is when the C1 is equal to 0, we usually call this Calabi-Yau variety. And the last one is when C1 is negative, so we call it canonical polarized variety. So I'm not saying these are the only generalization of Poincaré uniformization theorem to higher dimension, but arguably, I think these are the deepest like perspective to generalize the uniformization to higher dimension. I mean, in complex geometry. So in this like a trichotomy, when you have a different signs of the chain class, the kind of metric you want to search for is called a Kalan-Einstein metric problem. So basically, you want to find a Kalan-Einstein metric, which is a Kähler metric omega satisfy some kind of Einstein equation. So in this Kähler manifold case, it can be written as Rho omega is equal to lambda omega for some constant lambda. So you can always rescaling this lambda. So basically, it only depends on psi. So the psi could be positive, could be negative, could be 0. Also, let me remind you that because it's a Kähler manifold, the omega is a Kähler class. The Rho omega is also a closed form, and the homologic class given by this, the Rho omega is C1x. So particularly if you look at the equation, Rho omega is equal to lambda omega. If you take class of both sides, that just say C1x is proportional to the Kähler class. So particularly this, I mean, if the lambda is 1, that just say the C1x should be positive, lambda is equal to 0. That's just flat case, rich flat case, and the lambda equal to 1, that's just the C1 negative case. So you say that this way, when we study a Canalisan problem, it basically coincides with our trichotomy in higher dimension. So now we come back to this question to find such omega. So when lambda is equal to 0, this was solved by Yao. And when lambda was -1, this was solved by Albert and Yao independently. But arguably, the most interesting case is when lambda is equal to 1, because unlike the case lambda equal to 0 or -1, where we always have a solution, so we can always find a Canalisan metric. When the case lambda is equal to 1, this is not always true. Actually, there is an obstruction there. I mean, there is an obstruction which people know from many years ago. So that is when the variety has Canalisan metric, the automorphism group has to be reductive. This was first found by Matsushima. But for final variety, I mean, there are many examples whose automorphism group is not reductive. For instance, I mean, famously, if you blow up 1 point or 2 points on P2, you can calculate the automorphism, and you usually say it's not reductive. But there's but this is not the only obstruction. So this is the obstruction I think can be seen in the most in the easiest way. But that's not the only one. Later we will say there are much deeper ones. But on the way, Futaki showed that if you have some X which has automorphism which contains Gn, then you can define a Futaki invariant which depend on this variety and depend on this GM action. And then X has Canalisan metric implies that this Futaki invariant must be 0. So again, it's not if and only if condition, it's just obstruction. So if Futaki invariant is not a 0, then you can say X doesn't have a Canalisan metric. So then another theorem, which is Canalisan metric is nice, was proved by Bando Mabuchi, where they prove that the Canalisan metric is unique up to automorphism. So somehow, basically, they just say that the manifold, the complex manifold, if it has Canalisan metric, it's in some sense unique. So let me quickly explain some different geometers' work on solving this Canalisan problem. I mean, I'm an algebraic geometer, so I will not go into too deep details about this. But I just want to basically describe you some kind of analog of the thinking, which goes back to different geometers and some later development completely from algebraic geometry viewpoint. So as we all know that the Didi-Bar lemma says that if I have 2 Kähler metric which have the same Chern class, then the difference can be written as Didi-Bar phi. And similarly, now we are in the case that we assume the omega 0 is in the class of rich omega 0. So the class of omega 0 is C1x. That's a case we are interested to find the Canalisan metric. That's a case lambda is equal to 1. Then we know lambda, because omega 0 and the rich omega 0, they are also in the same class. Then the difference, again, by Didi-Bar lemma can be written as I Didi-Bar f for some f. And now, if you write down the rich omega equal to omega, you use this omega 0 and this phi and f, it will become a complex Monge equation, which is of this form. So in other words, to solve this Kallenstein metric, it's equivalent to find, I mean, here, F is given, omega 0 is given, the only undetermined thing is the phi. So you want to find the phi such that this Monzampe equation holds. So I mean, of course, this is a highly nonlinear PDE, but to find such Kallenstein metric, we boil down to solve this Monzampe equation. And you know, when you want to solve PDE, one typical way to solve it is we try to write some functional such that the solution will be some critical point of this functional. I mean, this is a very typical way of solving PDE. Here we do the same. So we consider all possible solutions in the space of Kähler metric, which has the same class as omega 0. So by DDR lemma, that just all smooth function phi such that this is positive because this is a Kähler metric. I mean, obviously, this is an infinite dimensional space. And then Mabuchi wrote down energy function. I think at that time he called it a K energy function. And I think now people usually call it the Mabuchi function. Is that, so it's some function, I mean, the explicit form of the functional is not important to us. But the key is that the critical point of this functional gives a solution of the complex Monzampe equation. So in other words, we can find the Kallenstein metric. So the upshot here is that solving the Kallenstein problem is equivalent to show that this Monzampe equation, this Mabuchi functional has a critical point, which must be a minimum for this functional. So in other words, the problem of finding this metric, we reduce it to find a minimizer of some functional or some infinite dimensional space. And later Dean wrote down a similar functional, I think nowadays it's called Dean functional, which has the same property that KE exists if and only if this Dean functional has a critical point. So there are some basic properties we know about this energy. For instance, it's convex along geodesic. So this basically gives the uniqueness. And you know, when you do this kind of PDE, I mean, often the space of all smooth functions is not good enough because you want to count, you want to make it to be a complete space with respect to some metric. The typical, I mean, one way is to do this to make it to be a Sobolev space, and later we will talk about some other completion. And then in 1997, Tian showed that the properties of this functional implies it has a critical point. So in other words, we instead of, I mean, for the purpose of finding Kallenstein metric, it suffices to check whether this functional is proper, has properties. But to us, I think what's more important is that Tian also developed a number of geometrical approach to attack the properties. So here the properties is still, I mean, some kind of different geometry condition. But in the same paper, Tian also wrote down some kind of like a geometrical way to think about this condition. And here, what I mean by geometry. So the slogan is that geometry is stability. So in other words, Tian developed some like a stability type condition to say that they imply properties and therefore they imply the Kernel metric, and also the other way. The Kernel metric implies those stability conditions, which I will go into details later. Go into more details later. And so somehow I think in this paper, in this famous paper, the stability, I mean, really become clear to play a very important role in the solution of Kernel problem. So, but let me just give you a 5-dimensional example to explain why stability will play such an important role in this problem. So this you can think about it as a prototype of all what we want to do. So the setting is we have a reductive group G, which is a compactification. Is a compactification of some compact group K. So K here is a compact real Lie group, and this G acts on a polarized manifold XL. So it acts L and with a linearization L given by some like ample Lie bundle, and we can always find the K invariant norm on L because K is compact. So now we define a function for adding X. So for adding X on this manifold, so for adding point X on this manifold X, we can define a function from G mod K to R, which is just given by, for any element G, the value is just a log of G acts on X hat. So X hat is some like a non-zero lift of X into L. And because the group acts on this L, so it will move this point around. And so G sends this point to somewhere, and the norm of that point will be my F. And because it's K invariant my norm, so it doesn't depend on K. So that's why the function can be defined as on G mod K instead of just on G itself. So now we look at the one parameter group C star of G. And we know that these are just this gives geodesic on G. And one can easily verify that this function F is actually convex along this geodesic. And so now come to the picture that the F is a function, it's convex along all geodetic directions. So my question is whether the F has a minimum on this open manifold G mod K, this non-compact manifold G mod K. So then one can prove that it has a minimum if and only if along every geodesic, the slope at the infinity is positive. Because if the slope is negative, then the point will the value just will become smaller and smaller along some direction. So somehow you say that, and because of this convexity, we know that actually the positive slope at the infinity will imply there is a minimum. But this slope at the infinite, indeed, it's actually an algebraic quantity. So it's just given by that. Now if you have this ray, this group also acts on X, and there is a limit which is X0. Then because X0 is the limit of this one parameter group act on X, so the L respect X0 gives a one-dimensional representation of C star, and which is just determined by its weight. And this weight is precisely this derivative, the limit of the derivative when t goes to infinity. So in other words, if we put all of this together, let's just say F has a minimum if and only if the weight is positive for all C star in G. So this weight is the limit of this C star X on X. So for that weight, you check whether it's positive or not. But by Hilbert-Mumford criteria, we know that this condition is precisely equivalent to say that X is GIT stable, the geometric invariant stable. So you say that the question of whether there exists a minimum is equivalent to. So this seems to be a different, like a completely analytic condition is equivalent to some sort of algebraic condition. There are two algebraic conditions. The first is given by this one parameter subgroup description, and by Hilbert-Mumford criterion, there is nicer way to say this is basically says X is GIT stable. So come back to our question. We want to also want to say whether some functional in some infinite dimensional space has a minimum, and now we want to relate to some stability condition. Now, of course, since everything is infinite dimensional, this picture becomes much more involved to define. So historically, I think Yao first had this insight that this existence of Cartesian metric should be related to some stability theory. But I think he never really spelled out what was precisely the stability theory means for final variety. So as I just said, there was just like a finite dimensional prototype example, and also a similar theory was worked out very successfully for vector bundles on smooth scalar manifolds, which says that a vector bundle has Hermitian-Einstein metric if and only if it's slope stable. So this is called the Hitchin-Kobayashi correspondence, and it's actually proved by Donaldson, Ulrich, Yao. So this vector bundle version is very successful. So it also inspired Yao having this insight. I know there also maybe some other reason. But I think Tian's paper in 1997, which I mentioned a few minutes before, was the one really spell out what the stability condition should be. So he basically, in this like a 5-dimensional example, there are two layers of stability. One is just looking at all the C-star subgroup of G. And another one is this like more global one, which is GIT stable. So, but actually the GIT is not the right notion for final variety. So somehow we should more rely on this one by just looking at the all C-star degeneration. So in other words, this C-star, you can think about this C-star axon Chow variety or axon Hilbert variety. You are asking some sort of question about this action, whether it's stable or not. I mean, very roughly speaking. So then if you pull back this family from the universal family of inside Hilbert scheme, you got a family of variety X over A1, such that the over genetic point, this is the GM equivalent family, such that over the genetic point is X, the final variety you look at. And Tian actually had the insight to say that we only need to look at the special fiber, such as the special fiber itself also is somewhat nice. For instance, it has the normal singularity or even has better singularity. So that we can also define Fataki invariant on the special fiber. Remember, now the special fiber has a GM action because 0 is a fixed point. The GM action lived on the special fiber. So that under this setting, we can define Fataki invariant. And Tian said that if you have a KE, the Fataki invariant is always non-negative for any such kind of GM equivalent family, such where X is a genetic fiber, is a general fiber. And the equality holds if and only if that the x is equal to x0. So basically, Tian proved that the either direction in this paper that the KE implies this kind of algebraic condition, this numeric condition, and he just also used this numerical condition to define the corresponding stability notion, like a semi-stability, polystability notion. But in Tian's definition, the Fataki invariant was the original Fataki invariant was the analytic definition, and in 02, Donaldson reformulated Tian's definition of Fataki invariant by just using algebraic terms. So here, when I write a red using red color, that's algebraic term, and the blue color is the analytic term, and this is in this page. So, but after all, you put all this together, the conjecture made by, I mean, what people call Yao-Tian Donaldson was for final variety, it has a color symmetric if and only if it's K polystable. So here I'm not going to, I haven't really defined what this notion means, but somehow the right-hand side is some algebraic condition, and the left-hand side is some metric condition. And I hope my explanation give you some feeling of where this conjecture came from. So this was the mathematicians who made this conjecture. So now let's talk about the results. So basically the conjecture become a theorem now. So first, as I mentioned, the Tian proved the either direction that the KE metric implies the K polystability. So when Tian proved it, he proved it for manifold, and then later Berman proved this for even for the singular case. And then the much harder direction is you assume the algebraic condition you want to get this metric. And in the final, again in the smooth case, that was first proved by Chenyang and Sun and Tian independently in 12. And but their approach so far only works for the smooth case. So you want to do you also want to cover the singular case for some reason, which I will explain, for instance, like a construct moduli space. So in the singular case, the proof can be split into two steps. So the first step is the so-called birational approach, initiated by Berman, Box, and Johnson, and completed by Li Tianwan and Li. They say that there is an algebraic condition implies KE, but this algebraic condition is not the uniform K-stable condition. Sorry, it's not the K polystable condition, which was the original YTD conjecture. But it was something called a reduced uniform K stability. So it's kind of a uniform version of K polystability. So you might ask, why the second theorem is still a theorem to say some algebraic condition imply the existence of K metric. So it's just as good as the first one, but actually it's not. You will say that in some sense the second metric means some of the most important recipes for us to understand the family of final varieties. But nevertheless, if you want to do YTD conjecture, the remaining part is completely algebraic, so that this uniform version of K polystability, which I call it a reduced uniform K stability, is equivalent to K polystability. And this was proved by Yuchen Liu, Zhiquan Zhuang, and myself last year. But the last part, again, it's in red color, so it's a completely algebraic statement. So I want to explain a little bit about this, give a very quick sketch of all these approaches. So the CDS-10's work, in some sense, actually on the differential geometry side, it actually gives more information than you combine the two theorems downstairs. So, but the downside of that is it only works for the smooth case. But the extra information given by the CDS-10 was completely in a different geometry level. So in the algebraic geometry level, the result which follow from all the results follow from CDS-10 can also follow from the two theorems later, but the two theorems later can also cover the singular case. So that's kind of the difference. So let me quickly explain what goes into the CDS-10's proof. So that's what people call cheaper coding 10 theory. So basically, if you have this is not exactly the proof, but what's the most important recipe in the proof is that if you have a sequence of Fano manifold with Cayley symmetric, there is a way to construct something called a Gromov-Hausdorff limit, which is a metric space. So, but the key is that we want to also realize this metric space by some algebraic construction. So the construction is that I choose the basis of this M, and I let this M has to be sufficiently large. Then for different choice of basis, I embed xi differently inside the Pn, right? Here, the choice of the basis, you have to be careful. It's a normal orthogonal basis with respect to the Cayley symmetric. So somehow the choice of the basis depends on the metric you start with. And then now if you different choice of normal orthogonal basis, they only differ by one element in the unitary group. It's not in the PGL. So in other words, the difference is contained in some like compact group. And now for every xi, I get a point inside this Chow variety, or let's say Hilbert scheme. And when you choose different bases, this point might move, but it's moved by only a compact group. And now I have a sequence of this, but goes into a subsequence, I can assume they have a Chow limit. And this Chow limit will not depend on the embedding. So in generally, of course, if you have a different family, if you move your points in your orbit, the limiting point might be not on the same orbit. So for instance, you have a family of P1, then the limit broke into two P1. Then the limit, the choice of sequence of points depend on whether the limit is on the first P1 or the second P1. But here, the point is the unitary group is a compact group. So when you move it, the limit will be also deferred by some like compact group element. So this way you really got a well-defined algebraic space. So which is just the Chow limit. And then you have to work very hard to prove that the algebraic space is actually just give you metric, the Gromov-Hausdorff limit, this metric space. So all the meat of this proof goes into identify the algebraic space and this metric space, and that involves a very deep analytical works. But from a layman's viewpoint, if we don't understand analysis. So just look at the outset of the proof. So the proof gives two key properties of this family of Fano variety. So first is say that if I have a family of Kallenstein Fano variety, I want to go to find the limit. I don't have to go. There is a uniform M, which has to be sufficiently large, but the uniform M. So I can only fix this M, then find the limit inside this ambient space. So that's I call boundedness. And another problem is that this sequence indeed has a limit, which also has like a Kallenstein or has a algebraic structure. So it's basically also lands in the class of varieties you want to study. So that is a compactness. So somehow I would say you can roughly think about this proof is that kind of the key point of the proof is kind of algebraization. So you have this metric space limit, you want to algebraize it into an algebraic variety. So you want to develop an algebraic process to find the algebraic limit and to say this metric is identical to your algebraic limit. So that's somewhat a kind of algebraization process. So now I want to discuss a little bit about this birational approach, which was initiated by Berman Brooks Johnson and later completed by Li-Tian Li, was that, so now instead of taking the Sobolev space to complete the space of function phi, you actually take the space of Puris-Sablow harmonic function. And you have this condition that the energy is finite. So you somehow take a different completion. I mean, as you know that when you do PDE or do any analysis work, if you take the different completion of your function space, you will have a completely different theory. So here the theory is also very different with the one we talked about before. So, but this space, E1, I mean, this Puris-Sablow harmonic function could have a singularities, but this space still has nice different geometries. So first it has like a D1 metric. Second, I mean, it has geodesic to connect 2 points. And then it also, I mean, you can define Mabuchi and dim, you can extend the Mabuchi functional, dim functional to this space, and the convexity still holds. So again, with all these properties, what's left is to understand what happens at the infinite place. Remember, now we have a metric of a geodesic, we have a convexity of the functional. So to get the critical point, after many work, essentially you have to understand what happens when this functional, I mean, when you take the value of the functional along a geodesic, when the geodesic goes to infinite. So I think what was the key observation by Berman Brooks Johnson was actually the infinite place, you basically have a translation from the Archimedean world to the non-Archimedean world. So what happens is that you can actually, for this geodetic array, you can attach a non-Archimedean version of dim functional, and also a non-Archimedean metric, whatever it is, but just some object to say that this slope is bounded by this dim functional, non-Archimedean dim functional on this non-Archimedean metric. So somehow the right-hand side, whatever it is, but it looks very much like the Archimedean case formally, but I just add a NA, which means non-Archimedean on everywhere. So once you have this, no, our goal is to find some condition to guarantee the slope at the infinity is always positive. Then, of course, you can just assume that this is positive. And for that, we just say that this is going to say uniform K stability. And this will imply the existence of K metric. And actually this setting works for even singular final variety. But the main difference is that now, instead of the positivity of the Fataki invariant, which you can think about it as kind of like an analog of smooth function on the on the algebraic side. Now you have to assume the positivity on a larger space on this like a non-Archimedean space. So if you are, I mean, if you just want to find the algebraic condition, this non-Archimedean itself is algebraic, but somehow it's not the Hartung type algebraic geometry. It's more like the non-Archimedean type algebraic geometry. But for some reason later, for instance, when we want to construct a moduli space and so on, we really want some positive condition. What our condition is only on this Hartung type algebraic geometry, not this non-Archimedean type algebraic geometry. So then we have to prove this to our equivalent. So that's what we did. So what we really need is a polystable version of this, but let me just explain the K stability version of this. So we prove that the uniform K stability is equivalent to K stability. So far, I haven't defined anything, but what I want to say that there is a different way of characterizing K stability using divisorial valuation. So we can define some number called delta x, which is just infimum of some function defined on divisorial valuation, which I will give you the definition. This is A over S. Putting together is just some function on divisorial valuation. Then the uniform K stability is equivalent to say the delta is at least 1. So the infimum is larger than 1. K stability is equivalent to say each value is at least 1. So you have to prove that each value is at least 1. So it's larger than 1. Implies its infimum is larger than 1. So in other words, you have to show that this infimum is realized by some valuation. So again, you can think about that this infimum is taken in some like a non-Archimedean word. But for our purpose, we actually want to kind of like regularize this non-Archimedean object into some like a more traditional algebraic geometry object. And that's what we want to do. So this is kind of, you can think about it as kind of like a regularization process in the algebraic geometry. You know, in the PDE side, you first have a weak solution. You regularize this to make it to be a smooth, at least along the smooth locus. But on the algebraic side, we also have this regularization process to regularize this like a non-Archimedean object into some more standard algebraic object. So that's what I'm saying, like this more traditional Hartung type object, you can think about it as analog of smooth function. So this regularization process is quite deep. So first, you can define this function A over S, not just on E, but on all the valuation space. So you enlarge your space, that's like you solve PDE. You want to find a smooth solution. You first find the weak solution. You enlarge your space to some like then you find the weak solution there, and then you prove the regularization process. So here we also first enlarge our space, and then one can prove without too much difficulty that this delta x is computed by some valuation. But what's much deeper is this valuation. Indeed, you can first prove it's a cosine monomial valuation. so this is some slightly more general valuation than dividend valuation. But the proof of this theorem by Bloom, Liu, and myself already use the Burkhardt proof of the boundaries of complements, which is the main theorem in his paper in 2015. So this step is actually already quite deep. But this is the first part of the regularization process. We got a quasi-monomial valuation. And then the second step is we prove there exists a dividend valuation such that this delta x is really calculated by this dividend valuation. And here we have to prove some like a finite generation, some like a completely new type of finite generation theorem. And this was done by Liu and Zichuan Zhuang last year. So before I give the break of the first part, let me just quickly define what A and S is. Remember, this delta is an information of some function defined on E. This function is A over S. So A is just a standard log discrepancy function. So this function appears a lot in minimal program. So somehow this, you say that there is a deep connection of the caseability and the minimal program. So here we see the first evidence. And we basically works on the quantum variety with KLT singularity, which is equivalent to say that the log discrepancy is always positive for any E. So yeah, I mean, if you haven't heard this kind of log discrepancy, I think maybe first look at a little bit strange. Then you can just think about it as a smooth manifold. The quantum variety is smooth. Then this log discrepancy is basically just when you choose a birational model, you pull back your coordinates, then the change of the Jacobian will vanishing along this E at some order, and that's just the order. So this is just the order of the Jacobian when you change the coordinates. And the S function is so-called expected vanishing order. So minus K is some ample divider, so it will vanishing along E. I mean, and there is some large multiple will vanishing along E. So we want to measure like how much it vanishing along E. So basically this is measured by volume by minus X minus TE, and you integrate this and you average it by minus K, the self-interest of minus K. So this can be considered as a expected vanishing order. And A divided by S is our function to define, I mean, the informal define delta, but A divided by S is the function divided on all the dividend valuation. And both A and S can be easily extended to all valuations. So this function can define on all valuations. And then we want to start to basically the algebraic geometry approach is to start with this function on this space of all valuations. We want to find the minimizer, and then we want to prove the minimizer has all the regularity we need. Okay, I think this is my first part half.
Wait, thank you.